Okay, we are at section 25.4, energy stored in a charged capacitor. Uh, if you were in lab last Wednesday, I was discharging, I was quickly discharging the capacitors in the experiment by just touching both leads with a wire. If that were a large enough capacitor with a large enough voltage, you would have seen a spark. But we were working with 5 volts, and those were small capacitors, so there was no danger in it. If we share the um, PowerPoint, this discharge is discharge from just a camera capacitor, for the capacitor to charge the uh, flash unit. So they can be pretty spectacular. So know what you're doing before you discharge a capacitor. It's better to discharge it through a resistor, so there's no instantaneous current. But the point is that there is energy stored in a capacitor. You've got charge, you've got a voltage across it, so there is energy stored, and we're going to study that. Here's a parallel plate capacitor hooked to a battery and a switch, and when you flip the switch, you create an electric field, and the electrons move from one plate to the wire, and so you get a excess of electrons on one side and a scarcity of electrons on the other side. So you end up with a charge on the capacitor. And so we're going to look at that. The work required to move charge dq through the potential difference delta V across the capacitor plates is given approximately by the area of the shaded triangle, the area under the curve. So dW is equal to delta V dq, delta V being Q divided by C. So you get Q divided by C times dq. So the work is the integral from 0 to Q of QC dq. The capacitor is a constant, so we can pull it out. 1 over C times the integral from 0 to Q of Q dq, and you end up with 1/2 Q squared divided by C. And this is an important, this blue rectangle here, I forget what the equation is in the text, but it's an important equation for you to memorize, and it's a different potential way of calculating different potential energies. Q squared divided by 2C, or 1/2 Q delta V, or 1/2 C delta V squared. So that's I'll do some example problems using this, using two out of the 3 equations. So the capacitor is epsilon 0 times the area divided by the distance separating the plates, and V is equal to ED. So the electric potential energy is 1/2 epsilon 0 A divided by D times ED squared. Well, you'll see that the D in the denominator takes away one of the D's in the ED squared. So you have 1/2 epsilon 0 AD times the electric field squared. So the density, I'm drawing a blank. The energy density, U sub E, is equal to 1/2 epsilon 0 E squared. Okay. You have 3 capacitors and a battery. In which of the following combination of of the three capacitors is the maximum possible energy stored when the combination is attached to the battery? Well, if you put them in series, we know that if you put them in series, that the charge is the same on each capacitor. And if you put them in parallel, each one of them will have the voltage across each one is the same. So you can actually maximize the energy if you store it if you have it in parallel. So that's the answer to that question. Now, the defibrillators use a large capacitor to actually store enough energy that's greater than the battery voltage, and it's used to deliver a large pulse to the patient. And if you need to do it more than once, you have to wait a little bit. You can it stores up to 360 joules, so it can deliver the energy in 2 milliseconds. So other devices use the storage capacitor. The flash battery is used, or capacitor is used to have a large burst of energy for your camera flash. And it says lasers used in fusion experiments. These are some of the applications where a capacitor allows for a large storage. Also, you have the earth can act as a capacitor. The surface of the earth is one. The surface of the earth is one plate that's negatively charged, and the other plate is a spherical shell where average positive charges are located in the air, and it slowly leaks. But a lightning strike will return will charge up this capacitor. Okay, the next we're going to discuss capacitors with dielectrics.